From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning, everyone. Today, I guess, is a very sad day because we can't talk about... In fact, I don't want to talk about basketball anymore. So, but we'll recover by halfway through Optics 513. We can talk about basketball again. So. Anyway, I had a nice week in Hawaii last week, working very hard, of course. I went to a meeting on astronomy. I gave a course in optical testing, but what I found out about these astronomers are certainly using interferometry all the time now. That's a very, very hot topic. And I knew they'd used it for a long time, but I didn't realize all the fantastic white light interferometers that they plan to put up in space, for example. Incredible. Of course, I don't know if any of you are young enough actually to live long enough to see these systems working up there. They really talk about what they're going to be doing the next 100 years or so, I guess. Anyway, it was a very interesting meeting. So I guess it's been 2 weeks since I taped my last class. I can barely remember what I talked about then. But I guess we were talking about Talbot Images, and I'm going to repeat a little bit of what I said before. I'm sure all of you have watched the tape, and you don't need to have me repeat it, but I need to repeat it so I can remember what I said. So anyway, Talbot Images are really, they're a fascinating thing. And I gave you the reference here, Goodman's book. I'll just repeat that again, 4.5.2. where he goes through Talbot Images, but he does it in a little different way from what I want him to do. He looks at it in terms of transfer functions and calculates where the images are that way. I wanted to think more about it, a little more physically about it than what he does. So let's say we have a grating here, which has a transmission function, T sub A, just a sinusoidal or cosinusoidal grating. 1/2 times 1 plus m cosine 2 pi squiggle over L. And so we have this grating here. And the period here, well, goes through 2 pi over distance L, so the period is L. And we're going to go over here some distance z away and look at what the amplitude or intensity is over in this plane. Now, if we illuminate this with a plane wave, we're going right down the axis here, if we go just to the right of the grating here, the amplitude or the amplitude distribution can be written as this times whatever it was we illuminated it with, plane wave in this case. And so we could write here that right after the grating, u of squiggle and eta 1/2 1 plus m, and I guess it's m over 2, times e to the I, 2 pi squiggle over L, plus e to the minus I, 2 pi squiggle over L. Okay? So I'll just expand the cosine and e to the I and e to the minus I. Now, if I look at this here, what it looks like is a plane wave. Okay? And plane wave propagating along, and we often think of the plane wave, we can just write that as e to the I, 2 pi over lambda squiggle sine theta. So theta is the angle that this plane wave makes relative to this z-axis here. And this guy is the same thing, except be a minus sign here instead of a plus sign. Now we're going to make the approximation here that the angles are small. And so I'll say theta small. And so we could write this plane wave then as e to the I, 2 pi over lambda squiggle times theta. And so we have 2 pi over lambda squiggle times theta was this 2 pi squiggle over L. And so we get theta is lambda over L, or for larger angles, sine theta is lambda over L. Okay, what we want to do now is, as this propagates along, we want to calculate what the distribution is. And this next part is kind of the, I won't say tricky part, but it's a little bit different from what you might first guess. And we're going to treat this as a plane wave spectrum here. So after we illuminate this grating with this plane wave, we get a plane wave that goes right down the axis, so that's the first guy here. And then we're getting these 2 plane waves here, leaving at angles plus or minus theta. Now, if we propagate between 2 planes here, distance z apart, and we propagate here a wave at some angle theta here. We've gone through this a few times in class, but it still maybe is a little surprising that the phase difference we're going to get when we go from here to here will go as 2 pi over lambda z cosine theta. And it's not z divided by cosine theta as you might first guess, but remember we went through this derivation back when we were looking at plane parallel plates and stuff and looking at the interference fringes there. That as we propagate along here, the phase is going to change as 2 pi over lambda z cosine theta. And so what we have here is that the phase change will be approximately equal to, again, small angles. So it's 2 pi over lambda z. And for small angles, the cosine theta we write as 1 minus theta squared over 2. And so that's equal to 2 pi over lambda times z minus 2 pi over lambda z. And theta up here was lambda over L. So that's lambda squared over 2L squared. So we could write that as 2 pi over lambda z minus pi lambda over L squared times z. And so if we go back here and we propagate it along a distance z, and we started out with this for the amplitude over here, what we're going to have for the amplitude variation in this plane of z, distance z away, will be u of x and y is 1/2 just a second, I'm worried about something here. Yeah, okay. Is 1/2 e to the I kz times 1 plus m e to the minus I pi lambda z over L squared times our cosine again, 2 pi x over L now. Okay, so we're getting this phase difference here that goes as, well, pi lambda z over L squared. And so we could square this to find the resulting irradiance. And we're going to get 1/4. And this constant phase factor out in front is going to go away. 1 plus 2m cosine pi lambda z over L squared cosine 2 pi x over L plus m squared cosine squared 2 pi x over L. That's the end of it. So we get this. This will be our irradiance distribution after we propagate at distance L. I mean, maybe you say, so what again? So let's look at some interesting cases here. And there are actually 3 kind of interesting cases to look at. The first case, oh, it's 2 pi x over L. So it's the same thing we had back here, except I've gone to the xy plane, and so this squiggle became x. So I'll just read this out again. 1/2 e to the ikz times the quantity 1 plus m e to the minus I pi lambda z over L squared cosine 2 pi x over L. And then we have multiply this by the complex conjugate to get the irradiance. So we get 1/4 plus times 1 plus 2m cosine of the pi lambda z over L squared cosine 2 pi x over L. And then the last term will be an m squared cosine squared 2 pi x over L. So this is a little messy, but there are 3 interesting cases here that turn out. And the first interesting case will be when we propagate a distance z such that pi lambda z over L squared is equal to 2 times some integer times pi. So that says we have propagated a distance z equal to 2n L squared over lambda. And we take this and plug this up here into this, and what we get then is that I of x and y is 1/4 times 1 plus m cosine 2 pi x over L squared. So what has happened is that after we propagated this distance here, we got back to a perfect image of the grating. Maybe I should write that down. In fact, I'll write that down in red. How's that? Okay. So we have a perfect image of the grating. And the nice thing is, we didn't even have to have a lens designer present because we have no lenses are being used. Okay, so no optics. We just take this, illuminate it with a collimated source, and we come over here the right distance, and we get a perfect image of that. Pretty neat, okay? And the distance we come is some integer times 2 L squared over lambda. And this is what we call Talbot images. Okay. And Talbot, I assume, is the person who actually discovered these and first explained them, but sometimes it turns out it's whoever has the best PR department that gets the credit for it. So can't guarantee that he did it, but we'll give him credit for it anyway. Okay, so that's one interesting case. That's probably the most interesting case. But there are two more to look at. So for the next interesting case, let pi lambda z over L squared equal 2n plus 1 times pi. So we have an odd number of pi's here. And so if that's true, then z is 2n plus 1 L squared over lambda. So instead of n L squared over lambda is instead of 2n L squared over lambda is 2n plus 1 L squared over lambda. And if that's the case, then I of x and y, well, let's see, we come back here. What's going to happen? It's going to become a minus sign. And we're going to get a quarter times 1 minus m cosine 2 pi x over L. So this is a copy of the original grading, duplicates the original. We have a perfect image of the grading. However, we have the contrast is reversed. We have a minus sign here. So we have a perfect image of grading, but we have a contrast reversal. Okay. Again, no lenses being used. Just looking the right distance away, and we get a nice perfect image of this grading with the contrast reversed. And they also call these Talbot images. Okay. Item number 3, interesting case number 3. We'll say now let n lambda z over L squared equal 2n minus 1 pi over 2. 2n minus 1. Yeah, thank you. Just checking, see if you're awake. I'm still partially in Hawaii. Pi lambda z over L squared is 2n minus 1 pi over 2. Okay. M is going to have to be less than 1. And we're going to come up here, the original amplitude transmission, I didn't say this, but we're going to make that m is less than 1, so we don't, otherwise we'd have a phase that we would be introducing here. So I'll say m is less than 1, or less than or equal to 1, carrying all the way through here. Okay, so pi lambda z over L squared is, in fact, I did have that wrong in my notes. I might as well correct that. Pi. And I'll go back here. Okay, so this was the third interesting case. And so if that's true, then z here is what? N minus a half L squared over lambda. And if we now take this and plug this back into our expression, wherever it is, back into here. What we'll see then is that the cosine is equal to 0. So cosine of n lambda z over L squared is equal to 0. And I of x and y is a quarter times 1 plus m squared cosine squared 2 pi x over L. And we could rewrite that as a quarter times 1 plus m squared over 2 plus m squared over 2 cosine of twice the angle, 4 pi x over L. Okay. So we just rewrote this in terms of twice the angle and got this 1/2 m squared out front. So again, we get a nice image here. However, this image will have, what, twice the frequency of the original image, and the contrast is going to be reduced. Question?
But in with the cosine? The intensity?
No, I think that was when we come back to the expression here for the intensity. We've I squared here, but this is no square on it. And now we're simply saying that this cosine here becomes a 0. So our expression becomes this. Well, let's go back and look at case 1 here. Yeah, in case 1, what we put in here was that this quantity right here is 2n times pi, and so that is equal to 1. And so I could factor this out, make this 1 plus m cosine theta, cosine of this thing, squared. Or I could have gone right back up here and this became 1, and then I squared that. Oh, in case 2? Oh, now you found what my problem is. Case 2, I was again checking to see if you were awake, and I omitted the square. But I did have it right in my notes. I can't copy from my notes. Okay, so then here, the cosine became 0. If I go back here, so this cosine here became 0. So I got 1 plus m squared cosine squared. And then I used a trig identity to go from the angle to twice the angle. And so what we have here is, again, we have a nice image, but it's going to have twice the frequency of the original image. So this image has twice the frequency of the original image. And there's one other problem here. The contrast here, well, out in front we have a 1 plus m squared over 2. Here we have only an m squared over 2. And so we have reduced contrast. And if the original object were of low contrast, then this is of very low contrast, I guess I would say. So this is called a Talbot subimage. And if, in fact, this is a homework problem I've given sometimes in the past, maybe not this year, I forget. If m is much, much less than 1, then the periodic image will vanish at this subimage plane. So if we started out with high contrast sinusoidal pattern, we would end up here in this plane with a double frequency. If the original pattern had a very low contrast, then this will essentially wash out, and we will not see a periodic image at this plane here where z is equal to n minus a half L squared over lambda. So we have these three interesting planes here. Z was 2n L squared over lambda. Z was 2n plus 1 L squared over lambda. And Z was n minus a half L squared over lambda. And if we go, instead of use my little drawing here, let me just go to Goodman's book and use his drawing that he had. So here was our grading. We come along here to the right, and when we propagate the distance here of 2L squared over lambda, we're going to get a perfect image of the original grading. If we go twice that distance, again we get a perfect image of the grading. If we go half that distance, we get a nice image of the grading, but it's going to be phase reversed. Okay? If we go a quarter that distance, quarter of this 2L squared over lambda distance, or 3/4 the distance, that's where we get the double frequency image, the low contrast double frequency image. And so if we just look here in different planes, I mean, it's pretty neat. The image is going to keep duplicating itself without any optics at all in here. Now, have any of you ever seen this in the lab? One. Good. So it actually works, doesn't it? I'm thinking in the future I don't know if I have a lab with this course, but I need to have some type of demonstration, because this is, there's a number of things here we look at that are really very interesting, and this is one. It's kind of neat how it works. Put lens designers how to work, maybe, if you could just figure out how to use. Well, this works with almost any periodic structure here. It doesn't have to be just a sine wave that we've done it for, but it has to be a periodic structure. Any questions before we about ready to leave Fresnel diffraction? So do you all feel that you're experts on Fresnel diffraction now?
Function as long as it was repeatable?
Well, if it's repeatable, it's periodic. So there's actually a problem here in Goodman's book of showing that this will work not just for the nice sinusoidal grading that we picked here, but it will work for any periodic structure. And basically what you're doing, you're writing that as a Fourier series.
Period?
Well, length of the period. I mean, you want this grading here has to be large enough to have many periods present. And as you truncate the grading here, then you get some convolution effects here. So we're assuming we have many periods present here, and we're staying away from edges. Okay. Well, that's essentially everything I was going to cover on Fresnel diffraction. So we will now go to I guess I'll call it a very special case of Fresnel diffraction that we will call Fraunhofer diffraction. So it will take us to chapter 14. Well, we already have talked about the approximations for Fraunhofer diffraction. Oops. Spell that right. So what we're going to do, I'll get to a drawing here, which I didn't hand out, but it's pretty simple for you to draw. So we're going to start over here in some plane, and I guess at least for my drawing, I call it the x1, y1 plane. And we're going to have some aperture over here. And for Fraunhofer diffraction, we remember that we are essentially illuminating this aperture with a plane wave. We're assuming that any source on the left is far enough away that we can think of it as a plane wave. And we're going to go over here a distance z to the right and look at the diffraction pattern in some plane that I'm calling x2, y2. We're going to look at some point p naught here. And so if I have a point in the diffracting aperture P1, I'm saying that the distance from P1 to P naught is R01. And we already know from what we've talked about in the before in the approximations leading up to Fraunhofer diffraction, we're going to assume that we're far enough away compared to the size of the aperture that we can assume that we have plane waves leaving the aperture. And if I look here in a vertical plane here, I'm going to say that the angle, we can think of an angle of phi from an origin here. In the vertical direction is phi, and in the horizontal direction here, the angle will be theta. And we're going to, in a minute, write the equations for the diffraction in terms of phi and theta. Okay, everyone has the drawing. Now, I'm going to go through the binomial expansion another time because there's actually two ways that I want to go through this binomial expansion. So we can say that u and I'm going to go back here and keep consistent with my notes. My drawing here has something that, I guess in my notes, I'm going to call this x naught and y naught here. So let's change that. Okay. So we can write here u of x naught, y naught is what, 1 over I lambda. Probably dreaming about this after the basketball game last night. Minus infinity to infinity of u x1, y1, e to the I, k, r01 over r01, dx1, dy1. And what we're going to do here is that we are neglecting the obliquity terms, the cosine terms. And I'm also going to make this R01 here in the denominator, make it Z. And so Z is approximately equal to R01 in the denominator. Okay, so we'll just put Z there. And the cosine terms we've forgotten about. And so R01 that we have seen many times. Z squared plus x naught minus x1 squared plus y naught minus y1 squared. And we know we can expand that. We could factor out the z, and we could expand that as z plus x naught squared plus y naught squared over 2z minus x1 x naught plus y1 y naught minus this whole quantity over z. And then we had an x1 squared plus a y1 squared over 2z. And we get rid of this, and Fraunhofer diffraction goes away. Okay, so we all know that we could write it that way. However, today I don't want to write it that way. Okay? I want to do something a little bit different. And so we could also, I'll say likewise, we could expand this a little bit differently. And we could say that R01 is z squared, so I just multiplying that out, plus x naught squared plus y naught squared minus 2 x naught x1 minus 2 y naught y1 plus x1 squared plus y1 squared. Okay. Then what we're going to do now, I mean up here we did that essentially, and then we factored out a z and went through our expansion. But why not factor out this whole mess right here? Oh, yeah, you people are pretty sharp today. I think I should go away for another week again. Square root up here. You agree, okay? See, what was his name now? Let's see. Okay, so I mean, I'll factor this out. The more you factor out, the better the approximation is going to be. So let's do this. So z squared plus x naught squared plus y naught squared, and I'll remember my square root this time, times 1 minus 2 x naught x1 plus y naught y1 over, this whole mess here, z squared plus x naught squared plus y naught squared plus, the term I'm going to forget about, x1 squared plus y1 squared over z squared plus x naught squared plus y naught squared, square root. And we're going to let this go to 0. Okay. And so we have here that R01 is approximately equal to z squared plus x naught squared plus y naught squared square root minus x naught x1 plus y naught y1 over the square root of z squared plus x naught squared plus y, should be a naught there, y naught squared. So that's a little bit different from what we had above. Up above, our first approximation, we just had a z here. This approximation, we have square root of z squared plus x naught squared plus y naught squared. And so this is actually a little bit better approximation than what we had before. And so we could write this, that R naught 1 is approximately equal to z squared plus x naught squared plus y naught squared 1/2 minus x1 sine of theta minus y1 sine of phi. Okay. And so here we had tangents. Here we have sines. And sines are actually a little more accurate than the tangents. Okay. Of course, later we'll probably let sine theta equal theta, but in which case we will have gotten back to the same thing. But we don't need to right now. And so we've gained a little bit of accuracy by factoring out more here and ending up with sines instead of cosines. So we can write down here that go back to this equation right here for our Fraunhofer diffraction, and we can write that u of x naught y naught is equal to e to the ik square root z squared plus x naught squared plus y naught squared over I lambda z. Integral here, u of x and y, u of x1, y1, I should say. And then we have an e to minus I k x1 sine of theta, e to minus I k y1 sine of phi, and then we have what, dx1 dy1. Okay, so we got sines up here. And that's going to be the expression then that we're going to use for calculating Fraunhofer diffraction. This thing out in front, I guess I call that C right now, so I don't have to write it down all the time. Question?
What are x naught and y naught again? What coordinates are those?
So x naught and y naught are in the observation plane. So they would be the coordinates of wherever we're looking at this amplitude. Okay. So we now have the basic equation. I probably should draw a box around this. It's going to be a big box. Can't even get it on the screen here, but it's draw a box around it because this is going to be what the equation we're going to use now in calculating our Fraunhofer diffraction. So now the next thing is we want to look at some examples. And the first example will be a single slit. And so we're going to use a one-dimensional slit. Of width b. And we get to 14.2, then we'll give the slit 2 dimensions, I guess. So we're going to take this slit and we're going to illuminate it with a plane wave of amplitude u sub I. I was thinking, I can't talk about basketball, but what is happening today? What's the big thing that's happening in sports in Arizona? Diamondbacks, yes. We now have a baseball team. Unfortunately, I don't care beans about baseball, but anyway. Maybe I'll have to change. I'm going to have to like baseball. I used to like the Detroit Tigers, and they always done so poorly. That's why I don't like baseball. Anyway, so now u of theta. So instead of u of xy or x naught, y naught, we're going to go u of theta. And instead of, bring down that c from what we had before, so I don't have to copy it right now anyway. And the slit is width b, so we go from minus b over 2 to plus b over 2. And we go to u sub I. And we go to e to the minus I k x sine theta and dx. And those you who have had Gaskell's course can instantly write down the answer as, well, I guess we better work it out here. Well, you're going to write it down as a sinc function, right? But I haven't had Gaskell's course, thank goodness, so I'll plug along here. C u sub I. 1 over, so we just do this integral 1 over minus I k sine theta times e to the minus I k b over 2 sine theta, and then from the lower limit we get minus e. Now it's minus b over 2, so it's e to the plus I k b over 2 sine theta. And so we could rewrite that as, well, C u sub I, and what we would get a 2 sine k b over 2 sine theta, and divided by a k sine theta. And I guess we actually had an I, a minus I, both upstairs and downstairs, so I'll just leave that out. And so what I would do then, I guess, is to multiply this by a b over 2 and divide by a b over 2. And what we will get now is C u sub I, whatever it was we illuminated it with, times, say sine of alpha over alpha, where alpha is pi over lambda b sine theta. So we had a 2 pi over lambda and a b over 2, so the 2's cancel. And yes, right. Thank you. You guys are so sharp today. There's a b here that I left out. So C u sub I times b. Okay. So maybe I'll just write that down one more time down here. So I'll write that as C prime, so I don't have to worry about the b's and whatever. And just write it down here as the sine of k b over 2 sine theta divided by k b over 2 sine theta. And maybe I better, guilt feelings, I'll write down what C prime is. So that was b u sub I over I lambda z, and then we had the e to the minus I, e to the plus I guess I had, plus I k square root of z squared plus x naught squared plus y naught squared. Okay. And so the irradiance here, I is equal to, we'll just say normalized I naught times the sine of alpha over alpha squared. And one more time I'll write down the alpha as pi over lambda b sine theta. So we could make a plot of that if we wanted to. And so we can normalize this, well, it's I naught, whatever that is. And we'll plot this as a function of alpha. And so we're going to get something that dips down here to 0, comes back up, not so high, back down. Okay. And we're going to have these zeros here at alpha is equal to pi, plus or minus pi, or 2 pi. Okay? And so the first minimum, first min, when pi is pi over lambda b sine theta, or b sine theta this lambda. So b sine theta is equal to lambda. So the smaller the slit, the more this is going to be spread out. Because smaller b, the larger theta is going to be for our first zero. Large slits, theta becomes smaller for the first zero. Okay, any questions on that?
Horizontal angle we had from before?
Theta is if we have a slit. I'm assuming I have a vertical slit here. And theta would be the horizontal angle then. So it's perpendicular to the slit. Okay. So we saw the algebra on this, and I think, you know, those of you who've had Fourier optics will probably never go through this algebra. You just look at this and you can write down the answer. That's certainly a nice feature of the Fourier optics. And you end up with this sinc function here. Now, so we can go through the algebra and understand it, but let's see if we can kind of understand this physically. What is happening here? A little physical explanation. So we have a slit, okay, and I'll make it like so here. And I'll draw this here. Now, when we think of Fraunhofer diffraction, so we're going to illuminate this with a plane wave, and for my explanation here, I'll assume we're going right down the axis. And then I'll ask you later what happens if we go off axis. But say we're going right down the axis here. And so we have these plane waves leaving at different angles. So let's pick a plane wave leaving, and I'll change color here. Let's pick a plane wave leaving at this angle, whatever this angle is. Okay. And this is the center of the slit. There must be an angle here such that this leaves so that, and B is the whole width here. I'll pick a point right there and a point right at the center here. So B over 2 sine theta, so that's this path right there. If that's equal to half a wave, then the light leaving here and the light leaving there will be out of phase by 180 degrees, and they will cancel out. So I've divided the aperture into two parts here, and for every point in the lower part, I have a corresponding point in the upper part such that B over 2 sine theta is half a wave. And so they're going to cancel out. Okay? So at this angle theta, when this is satisfied, for every point in the lower half here, then I'm going to find a point in the upper half that is out of phase by 180 degrees. So that's why we get our first zero here. And the second zero is going to be where B over 2 sine theta is 3 half waves. And our first max, well, away from the central max here, is going to be when B over 2 sine theta is a wave. Okay. So without a lot of math, you can understand physically why you get these zeros. And if we went back to Fresnel diffraction, the problem with Fresnel in doing this is that with Fresnel we don't have plane waves leaving here. We have parabolic waves leaving here. And so I can no longer do just what I did here. And so with Fresnel diffraction, we don't get zeros out there. Fraunhofer, we get the zeros. Okay? Does everyone follow what we did here? A little physical explanation of If I were to illuminate this at some other angle, other than normal incidence, then let's say I were to illuminate it at some angle like so. So now my positions of the zeros would be shifted because now I'd have to take into account this path length plus this path length here. And when that was equal to lambda over 2, then I would get a 0. Okay. So any questions on understanding physically why we get these zeros in this sinc function? Ready to go on? Clean sheet of paper? Sip of coffee? So the coffee was cold today. I wonder why that was. It'd been sitting out there in the cold too long. So what was the temperature last night? Anyone know? Sunny Tucson? No. Okay. We talked about a single slit. We're going to do the same now, except it's going to be a two-dimensional slit. So we'll call this a rectangular aperture. And so we will start off here with a slit. So this is X, Y, slit here width B, or height B, I guess I should say. And we're using A for the width. Okay. So now we can go back and write down our equation here. U of x naught, y naught is, I'm going to keep some of this here right now, e to the ik square root of z squared plus x naught squared plus y naught squared divided by I lambda z. Illuminate with use of I. And one integral then would be minus a over 2 to plus a over 2 of e to minus I k x sine theta. And the other integral is minus b over 2 plus b over 2 e to the minus I k y sine theta. And we have a dx here and a dy here. And maybe instead of writing this u of x naught y naught, maybe I should say u of theta and phi, whatever. Oh, okay, the second one here is a phi. May not look like it, but that's a phi. Phi is in the y direction. So e to ikx sine theta, e to minus ikx sine theta, e to minus iky sine phi. And so, since we did our previous problem, we can just write this down by inspection here almost. That this is I naught times sine alpha over alpha squared, sine beta over beta squared. And alpha, pi over lambda, a sine theta, beta, pi over lambda, b sine phi. So we have sinc function, two-dimensional sinc function here. Okay. Now, I think what I better worry about here for a second is what is this I naught? I mean, often you just write it down this way and you normalize I naught to 1 or something. Well, let's think here for a second what I naught really is. And we've done enough work on the previous problem that we can almost just write it down here. I naught is going to be equal to, well, we're going to get a u sub I squared and from our previous problem we got we get an a and a b from these, so we get an a squared and a b squared. And we got a lambda z here, so lambda squared z squared. Okay. So it's just what we had in the previous problem here, but we have another dimension, so I had to put an a in. So that's our I naught. And I'll rewrite that as u sub I squared we could write as the radiance incident on the aperture, E sub I. So write that here, that E sub I is a radiance incident on the aperture. So we get an E sub I here. I'm just going to take one A and one B, AB. And down in the basement then I have a lambda over A. And I have a lambda over B. So I've taken one AB down there. And I guess I still have a Z squared. So if we think about that for a second, E sub I times A times B is the irradiance incident on the aperture. Times AB, well, AB is just the area of the aperture. So E sub I times AB is just how much light we have going through the aperture, a radiance incident upon it, times the area of the aperture. Okay. Now, if I look here, lambda over A and lambda over B, that's kind of interesting. The larger, well, say that the smaller the aperture is, the larger this number is going to be. Smaller the aperture, the more the light spread out, and so the less is the peak irradiance here. It's interesting. So we have power spread out through solid angle. Omega is lambda over A, lambda over B. I mean, it gives you a measure as to how it's spread out anyway, I guess I should say. And we think of the area of the viewing screen. Is equal to the solid angle. Remember, area goes to solid angle times distance squared. So it's omega, the solid angle, times z squared. So what we have here is that I naught is power per unit area. And of course that depends upon how much power we get through the aperture. And it depends upon how wide an angle the light spread out. Then the area of the viewing screen goes as how it's spread out, solid angle times the distance squared. That all kind of makes sense. Now sometimes when we look at diffraction problems here, instead of looking at the power per unit area, sometimes we look at the power per solid angle. So let I naught prime equal power per solid angle, unit solid angle. And so that is just going to be E sub I, A squared, B squared, over lambda squared. Okay. So E sub I, A squared, B squared over lambda squared, so we got rid of the Z squared here. So this would be power per unit solid angle. So you see it expressed sometimes irradiance. Sometimes when you look at diffraction problems, you'll want an answer in power per unit area. Sometimes you want power per solid angle. And sometimes you don't even worry about what the I naught is. Okay, any questions on that? Let me look here for a second, a minute, at the... I had a little handout that I gave you. I have fallen in love with Mathematica. I have to tell you, I play with it all the time here. And play is probably the right word to describe what I do with it. And anyway, this is just back to our diagram that we had before, and writing down that the how the irradiance goes is our two sinc functions, sinc squared functions. And I just made a plot here of, we could maybe zoom in a little bit on that. Don't need to see all the numbers up there, yeah. Anyway, made a plot here. We have two different, I picked an aperture where in one dimension the size was 10 lambda, and the other dimension it was 5 lambda, and just plotted the amplitude out here. And of course there's a factor of 2 in where we go through 0, since the aperture in the two directions differ by a factor of 2. And then of course I had to play with some 3D just showing that in the two dimensions. So this was amplitude, and as you're playing, you square it here to get the irradiance. And again, I mean, it's spread out nicely, the factor of 2, since the aperture's factors of 2. And then, of course, I had to plot this here. And plotting the irradiance down here works pretty nicely. So anyway, you can see this pretty nicely on the computer, or again, going in the laboratory and setting this up with different sized apertures gives you a nice feel as to how the diffraction works. But it's fun to play with it on the computer too. Okay, so we've talked about a single slit. We've talked about a rectangular aperture. So what would be the next logical thing to look at here? Well, probably a circular aperture. And we don't have time to do a circular aperture today, but we have enough time to start on it, so let's do that. 14.3. Circular aperture. So those who've had Gaskell's course and expert on Fourier optics, you already know the answer. What is the answer we're going to get here? Sombrero function. Never heard of such a thing. Only in Tucson do we have that. So let's see what we can do here. We're going to go through a little bit of the algebra instead of just doing the Fourier transform. So we're going to take an aperture here. It's supposed to be a circular aperture. Something like so. And nice thing about circular aperture, we have rotational symmetry. So we only need to look in one dimension here. And so we say because of symmetry, consider only points on x naught equals 0 axis. At least that makes it a little bit easier for us. So we can write here that u as a function of theta is going to be equal to, well, some of it we can write down from before, e to the I k square root of z squared plus y naught squared, and x naught is equal to 0, so I don't need to write that down, divided by I lambda z, and illuminating this with u sub I. And now I have to do the integral here. And the way I'm going to do that is that we'll say that center of the axis, center of the aperture, this is going up a distance y, let's say. Let's say we come up here. I'm going to break the aperture into little horizontal slits here. And so the radius of the aperture here, according to my notes, is capital R. And the length of this little strip here, well, right this second I don't want to calculate the length of it. I'm just going to write that down as u prime of y. And the width of that little strip is dy. So my integral here is going to become, as I'm integrating over this, it's going to become the integral of u prime of y, whatever that is, e to the minus ik y sine theta dy, and y will go from minus r to plus r. Okay? So we're just integrating over the aperture. Only interested in one dimension here because of rotational symmetry. We're going to integrate over that and by adding up or integrating up all these little strips here. And I guess the length of the strip, we have enough time to write that down, is that u prime of y then will be equal to 2 times the square root of r squared minus y squared. So that's the length of this little strip. Okay. And so what we can do is that we can now, and I'll do that. I have a minute left. Don't want to waste a second here. We can say that u as a function of theta then is going to be 2 times e to the ik square root of z squared plus y naught squared over I lambda z, u sub I, integral from minus r plus r square root of r squared minus y squared, e to the minus I k y sine theta dy. And so we'll have to wait now until bright and early Thursday morning to figure out how to solve that. So I will see you on Thursday. And I think what we have homework due on Thursday too. And so have fun doing the homework, I guess. See you later.